Hello, my name is Gavin Ledford, and today I'm going to be talking about carbon nanotubes and CNT FETs. So to start off, what are transistors? Transistors are devices that are used as amplifiers or switching apparatuses within a circuit. And there are three different types of transistors that we're going to be talking about. First, there's the metal oxide semiconductor field effect transistor, or a MOSFET as it is commonly referred to, a bipolar junction transistor, which is a BJT, and a carbon nanotube effect field transistor, or a CNT FET. So what are CNT FETs and why are they important? So a CNT FET is, as I said, a carbon nanotube field effect transistor, and the significance is that they include higher current density drive. They also operate at very high frequencies and are comprised of carbon nanotubes, or CNTs, instead of silicon. So researchers are looking into possibly replacing silicon in the future. So there are different types of CNT FETs. There's the Schottky barrier CNT FET, which is what we're going to be focusing on, a partially gated CNT FET, a MOSFET-like CNT FET, or a C-CNT FET. And C-CNT FETs are they're the most common type of CNT FET because their properties are very similar to those of MOSFETs. So now CNTs, carbon nanotubes, are sheets of hexagonal arranged carbon atoms rolled up into a tube of a few nanometers apart in diameter. There are two structures of CNTs, the multi-walled, or MWCNT, or the single-walled, SWCNT. The nanotube software that I used was the Schottky barrier CNT FET tool, and that was used to simulate the respective transistor. And throughout the multiple simulations that were run, parameters were altered to show variability in the design. So what parameters were there and that were going to be changed? There was a VDS and VGS points, which asked for numbers from 1 to 50. Initial gate bias, which was between negative 1.5 volts and 1.5 volts. Initial and final drain bias, which is like at the end and the beginning. They both called for between 0 volts and 1.5 volts. The oxide thickness, which was a number between 0.1 and 30 nanometers. The dielectric constant, which was between 1 and 30. The Schottky barrier, which is important to this specific transistor, was a number between 0 and 1 because it is a fraction of the band gap. And the temperature, which went between 0 Kelvin and 450 Kelvin. So why change these parameters, and what happens when you do? Well, the VDS and VGS points is within the graph that we are going to create. The more points that you have within the graph, the better picture that you get within it. So you had the option between 1 point per graph or 50 points. So I just maxed both of those out at 50 to where we got the best picture possible. The gate and drain biases were to demonstrate the different values of what the transistor may see if it's in a circuit design. So those were in different places for different values of voltages to see what it would be. The oxide thickness to show in design what would be more effective or what is not needed, because it's all about cost versus effectiveness, to see if you don't need as much oxide, you can cut back on that and save some money. The dielectric constant, which was changed for the same reasons, just to see what works best. The Schottky barrier changed depending on how big of a band gap you wanted. And the temperature simulated like how it may operate if it was at room temperature, or at colder or hotter temperatures. So first we worked on the gate and drain biases, and this is the first simulation that we ran, and you can see that the curve is very smooth. Now whenever you made the VDS larger, it cut off at this point. So that demonstrates that the lower the VGS, it had a better picture. And whenever you raise the VDS from 1 volt to 1.5 volts, it made the line straighter instead of curved. And then this is negative 1.5 and negative 1.5 for the VDS. And this one's much straighter even than this one. So the changes in the oxide, you can see the graphs here. So the original simulation for oxide was 4 nanometers, then to 8 nanometers, 16 nanometers, and finally 30 nanometers, because that was the upper limit of what we were allowed to enter. So you can see, for the most part, it doesn't change much, but it does slightly, as the oxide gets larger, it slightly flattens out. It's very small because this is only dealing in nanometers, which is a very small measurement of distance. So it's not as great of a picture as far as telling the whole story. The dielectric constant changes. This one was the most run through form of the simulation. So at first the dielectric constant was 5, then 10, 15, 20, 25, and 30, with 30 being the highest limit that we could go to within the tool. And you can see at 5, it starts out very flat. And as it increases, it slowly becomes more and more of a curve with a knee to where you can see where it flattens out at about 5 times 10 to the negative 5th microamps. The Schottky barrier, there were only 3 of these that were run at 0.25 or a quarter, 0.5 and 0.75 to show that the higher that the Schottky barrier number got, the flatter the curve was. So this was more curved, and this is the original value that was provided with the tool. So it shows the most likely normal curve, and then it gets flatter. The temperature changes, this was to show how it may operate. So this temperature was at 4 Kelvin, which is to simulate liquid nitrogen, 77 Kelvin at this graph for liquid helium, 300 Kelvin for room temperature, and 450 Kelvin, that being the upper limit of what the tool allowed. So as you can see, for the most part, these graphs actually stay very similar. So that can kind of show how these transistors are able to be versatile as far as the temperature didn't drastically alter them, even though these are vastly different temperatures that you would see in their operation, and it looks pretty much the same. So the conclusion, as I just said, CNT FETs seem to be very versatile. They run at high frequencies. They don't seem to really be altered all that much. You can see flattening of curves for the different parameters changed, but the overall, it operates the way it seems to be intended. And so, are they the future of transistors? Well, in my opinion, right now they are more expensive than silicon transistors. So you won't see anything in like the next year as far as seeing them being very common. They're kind of too fancy for what they are needed for. It would be a very long time for them to get inexpensive enough for a consumer to need to use this. So the silicon transistor is just not going to go away. It has its own use to where it will be used. It is a little bit less powerful, so it will be used in more common settings, while carbon nanotube transistors may be in larger, like in power plants and various different applications that are more industrialized. And so, wrapping up my final thoughts on the project, it was very interesting getting to use NanoHub to run the simulation multiple different times. The total number of simulations I ran was 18, and I was able to, it all created on the same graph, and I was able to switch between whenever I changed the parameters to see how the curve altered whenever you adjusted the parameters one way or the other. So that was very interesting, and I was very glad to have the asset of using NanoHub for this. Here are my references for this: the Science Direct on carbon nanotubes, where I used some information to describe what they were, and the actual NanoHub tool itself. Thank you.